Good day. We continue our lecture on the design for strength from the earlier class. So, we had just a very quick recapitulation of what we discussed last class. We had discussed about that maximum shear stress theory, which also is called as an Tresca theory. And what we have seen, that yielding would occur when maximum shear stress exceeds the shear stress at the tensile yield point. And in the on this regard, we found out what we did. We have seen that we got some relations, that if this is sigma A, sigma B, the envelope was something like this. I am having these values of yield point, sigma yield point. Anyway, you can give also minus sign over here, and these are also bounded by these things. And we got the equations of the form sigma A for a safe design, sigma B modulus for the safe design, and sigma A minus sigma B for the safe design, again comes out to be yield point. Well, sometimes we can also use an equality to get the extreme points in this particular graph. Well, so we go back to this other theories. Now, the next one, what we call as a distortion energy theory. This is also sometimes called as von Mises yield criteria. So, what it states, that yielding would occur when the distortion energy exceeds the value of the distortion energy at the yield point in a simple tension test. And this criteria also agrees well with the experiment. Now, prior to talk about this distortion energy theory, just have a look of a situation. Now, what is this one? Is that suppose we have a material under simple tension test. So, if we take up an element over here, so we know this element is represented, say a 3-dimensional look of the element. If we take, it is represented by this nature. Is correct? Now, this particular situation we can think of in this way. Before that, let me do one thing. It's just equivalent to okay. See, the total sum of the forces sigma 3, sigma 3, sigma 3, that gives you the total sigma. Here it is sigma 3 outward and inward cancels out, inward, outward, cancels out. So, this represents the total scenario. Now, what it is meaning physically? You can see this particular first figure is all under compressive, tensile forces, sorry, it is all under the tensile forces. Now, sometimes this is also called a similar situation of the what you have learnt earlier is that hydrostatic forces, as if it is acted upon by the hydrostatic forces. So, by this you can expect such situation will yield you a change in the volume. However, in this case you can see the situation, if we just view from one side, it is equivalent to what? This particular one compressive, another as tensile. It is just an equivalent to something like a shear or distortion of the element that is taking place. It is a case of the pure shear sort of thing, and this is also, if you look from one negative another positive, also it gives you some sort of a distortion in the shear sort of thing. So, that means what is happening, that this particular situation creates a change in the volume, and these particular situations create a distortion. There is no change in the volume, but the distortion into this particular element. Now, normally the genesis of this distortion energy theory came like that people found that under hydrostatic, particularly a material can take up a huge amount of hydrostatic forces, okay, but it fails, it fails. Then why it is happening? Because because if it is can take up a huge amount of hydrostatic forces, then why it is not able to take up something else, why it is failing much early. So, that gives an idea that it must be something else might be happening, and that is what the definition of distortion energy says. So, the distortion energy says is that the failure is due to the distortion energy or the strain energy, only that component of strain energy which is creating the distortion. So, one can very well find out that what is the total energy for some such scenario, and then from that if we can just if we can just find out this particular portion, the distortion energy portion, then what we get? That we get an energy due to distortion. That means we find out this one, subtract this one, and then we get the total distortion energy. So, once we can find out the distortion energy, then that distortion energy can be equated with the distortion energy when we compute for a simple material under simple tensile test. So, that is the idea. Now, once we go back to this one, says the yielding would occur when the distortion energy exceeds the value of distortion energy at the yield point in a simple tension test. Now, again if we see that this particular situation, that what is the distortion energy, without, as already we have learned that this particular distortion energy UD can be written as 1 upon 6 G sigma A square minus sigma A sigma B plus sigma B square. This is the distortion energy one can get by the process what we have just discussed. That means you just compute the portion which is creating a distortion, but not the volumetric change. Now, as usual, the sigma A and sigma B represents in a two-dimensional state the principal stresses that is occurring at a point onto the machine element. Now, when we consider this distortion energy at the yield point, okay, then what we get? We get 1 by 6 G. So, you understand, if it is a simple test, then only sigma will be present, sigma B is not coming into picture, and that sigma A we can write it as an sigma yield point square. So, if we equate these two, then we get the distortion energy theory. So, that means what is this one? That means sigma A square minus sigma A sigma B plus sigma B square is equals to sigma yield point square. Now, in this case, what we can consider is that if we are going to have a safe stress design, then one can consider that always the distortion energy is this one, and the limiting value again we can write it like this. So, this one what we understand by the mathematical representation of the distortion energy theory. So, the distortion energy at a point is less than the this yield point criteria. Now, if we try to find out that this, you can see this is a simple an equation of an ellipse, and so this ellipse what we are getting, if we try to plot over here, then what we will be getting is that again we plot a sigma A, sigma B, then we get, well, I will try to draw a good ellipse for you, something like this. Okay. So, this represents the value of the sigma yield point, and where you can find obviously this point will be the extreme points where it is a sigma yield point, this is minus sigma yield point, this is sigma yield point, so on and so forth. So, you get a major axis, and if we plot this minor axis, then this is the point we get. Once again it will be just exactly dividing, and this coordinate of the point will be what? That we get a value sigma A equals to minus sigma B, and if you substitute, then you will be finding out that this particular point will be coming out something like that. This is 0.577 sigma yield point. You can verify this result. Well, now this particular one is the, that means this is the envelope within which the stress in the machine element is in a safer zone, and that means in that particular case we should not consider this equality, and this equality means that just this is the boundary, all the stress points maximum it can up to the boundary, inside it is safe, outside it is unsafe. So, this is the idea of the maximum distortion energy theory. Now, this signifies a very simple situation what we did earlier in case of maximum distortion energy theory also, I am sorry, maximum shear stress theory, that if we have a simple tension test, okay, that means this comes out to be sigma A, this comes out to be sigma A only, and if we go up to the yield point, then in this case if we plot a Mohr circle, then we get a value sigma A like that, and this is a tau max. Okay. Now, if it is a tau max, then this is the value, that is a sigma A by 2. Now, let us substitute over here. What is the value of sigma B? That is not coming into picture. This is sigma A sigma b, and in this criteria this particular is coming out to the yield point square. So, if we substitute, then what is happening, then this we get is something like that. For a simple tension test, we get a value that sigma yield point sigma a by 2, that is we get, can I use a fresh page, we get a situation that sigma yield point square equals to 3 tau square. And this one, if we consider, then what we get? We get a value something like this. Okay, just one second. I think this is not very correct, I suppose. I'm just sorry. Let us do one thing. If we consider that this body, because tau yield point we have to get in other way, if we consider this particular situation as a simple tension, then what we have seen, that the Mohr circle comes out to be like this in a pure shear. Then this is your point where we get the value, this is a tau, this is a tau. So, this is your sigma a, this is your sigma b, and what you get, sigma a equals to tau equals to minus sigma b. So, if you put that result, then what we get, we get sigma yield point squared equals to 3 tau square. I am sorry, this is not, this is valid for the pure torsion. I would like to see, by mistake I just give you a tension, okay, because the tension case already we have discussed earlier. So, what you are getting, this particular value of tau comes out to be square root of 1 by 3 sigma yield point, and that actually is 0.577 sigma yield point. So, this is a very good result what we get from the experimentations. So, when we talk about the distortion energy theory, then as because it gives a close match with the experimentations, we have a very good idea that this particular distortion energy theory goes well in a design. So, if we just have a comparison for the same values, the stress level sigma a, sigma b, we found what is this one? Maximum shear stress theory. So, if we superimpose onto this value of one thing, that is this value of distortion energy results. So, distortion energy, and this is maximum shear. So, you find that this maximum shear stress theory is enveloped within the distortion energy theory. That means, this you understand, if we drawn this value was what, 0.5 sigma yield point, and this value is coming out to be 0.577 sigma yield point. So, these are the two situations. You can see that from here we can say distortion energy theory, is relatively less conservative compared to maximum shear stress theory. So, this is what are the two theories which we normally use for the design in the ductile material machine component. For the design of any machine component of the materials, as I told you, the ductile materials, these are very commonly used theories. Now, what we get, the next one is the maximum principal stress theory. So, if one of the principal stresses sigma 1 sigma 2 exceeds the ultimate stress, failure would occur. This is a very simple statement, and in this case I would like to point out that this is normally used for the brittle materials. This particular theory goes to some extent well for the brittle materials, and here if we use the denominations, just the same thing, I think we have used the value A, okay, it's, we can put this sigma, well, the white was better, okay, sigma A, and let us put this one as sigma B, and this is sigma A. Sigma 1 and 2 sigma 2 is same, but anyway, as we are using this notation sigma A and B to represent the principal stresses, it will be better that we use the same thing. Now, what I would like to say is that if we consider this theory, then theory simply gives you the limiting zone sigma A, sigma B, this point is sigma ultimate, and this is sigma ultimate as usual, and you understand this is also sigma ultimate. Shall we put a negative sign just to represent? Now, here sigma A, sigma B exceeds the ultimate stress. Now, this ultimate stress, what has been defined here is, to be more specific, when the specimen is in tension test. So, if it is in the tension test, then we get this value of the ultimate stress, and for which the failure will occur. Now, this particular theory has got a drawback. The drawback is this, that the theory says that the ultimate stress in simple tension, that means it takes into account that the ultimate stress value in the simple tension test and in simple compression tests is the same, but it is normally, it is not, because what happens when you use the brittle materials, then the flaws or some other material defects will be more pronounced if it is acted upon by a tensile test. But if it is acted upon by a compressive stress, or the compressive stress on the other hand, then what we will be finding out that the material can take up a more and more load. So, in general, as it has been earlier, last lecture when we have discussed about that materials, we have told something that the brittle materials normally have the more values in the compressive stress compared to what we get in the tensile test. So, just to overcome this situation, the drawbacks of this maximum principal stress theory, then what has been suggested is that another idea that is called Mohr's failure criteria. Now, what is a Mohr's failure criteria? Without giving any definition, let me draw and just explain you. Suppose we have conducted a test. Which was a test? First test is a tension test, second one is a compression test. Then we got a result. One is an ultimate stress or ultimate strength of the material, and another is a compressive test, which gives you an ultimate strength of the material in compression. And as I have discussed, let us consider the two situations, that these two situations reveals that suppose this is UT, you understand UT means in tension, and we got something, this is sorry sigma B, and this sigma something in compression, this is UC. So, this is UC. So, why this UC is larger? The same logic, that compression test results are normally compression test results gives normally a larger value compared to what in the tensile tests. So, we understand that any stress level, suppose any test levels within this will always give you a safe result. And this particular result, if we just try to solve, try to put it in a graphical manner, then what we get? That we get square UT and we get another square UC, this being sigma A, this means sigma B. That means we have undertaken one test in tension, the result is plotted. We taken one test in compression and this result is plotted. So, in both the cases, if you are either tension or compression, you are getting the values of sigma A and the sigma B, unique values of sigma A, another value of the sigma B. But what is the situation that suppose in one test you get, in the first test you get sigma A equals to some value, sigma B we are not considering in this particular case, and another one it is coming out to be 0. So, either sigma A is coming out to be ultimate, other case compressive. Suppose you are having both the values sigma A and sigma B, just the idea, if we conduct a shear test, pure shear test, then what we get? We get something like this. This value sigma B, this is minus sigma and this minus sigma. So, if we plot this particular value or this shear test results, then we might be getting another situation. Like this. Is it okay? Now, the Mohr's criteria is this, that if we draw a line touching this, so this is the what we call is the, this we consider the envelope of this one. So, this is the envelope for the Coulomb criteria, and this is the envelope of safe stress. So, if we plot the results where we are giving an opposite signs of the sigma A and sigma B, then what we can find out, that just like an maximum shear stress theory, we will be getting again these two lines. So, one is an sigma A well tension test, sigma A compression test to values. In this case we do not have any sigma B. Another one, you conduct a shear test, this value you put this profile. So, here you are getting a single value, that means sigma A positive, this one, sigma A negative, this thing, and if it is in both, then this is coming out to be the criteria for the Mohr's failure. Now, one thing I would like to say, that is in the Mohr's failure also, the material what the people considers is a brittle material. So, now what we have learned two situations. That means two situations means one for the brittle material, another for the ductile material. We discussed about the ductile material. The two popular theories are what? The maximum shear stress theory and the distortion energy theory, and for the brittle material we consider the situation which is called the Mohr's failure criteria and maximum normal stress theory. So, these are very important situations. That means these four theories, maximum shear stress theory, Tresca theory, distortion energy theory, this is for the, both are for the ductile material. Then next comes to the maximum principal stress theory, and then we find out the Mohr failure criteria. Now, with this what I just like to say, that let us try for a very simple type of problem which will give you some ideas that how we consider the two failure theories. Two failure theories, I mean to say two sets of failure theories, one for the ductile material, another for the brittle material. So, how it can be employed in the design, taking a very simple examples. Now, one of the examples is like this. You can see a 38 mm diameter steel shaft has yield strength of 250 megapascal, and determine the magnitude of T for which yield occurs. Now as because with our ideas, the steel shaft and yielding, these are synonymous. You understand the steel shaft is a normally ductile material, and yielding also a situation by the failure for the ductile materials. Now, one thing is that one has to be quite sure that while choosing in design the normally ductile, is it really ductile, something like that, means one has to be very sure about the materials he is using in the design. Well, that is a different situation. We will be considering the case later on when we will be going for the actual designs. Now, let us find out that how to do this particular, tackle this particular situation. So, first of all, we can see that this is coming out to be the shaft, and without drawing this particular free body diagram for the entire one, just we can see from here only, if we can consider a torque in this direction, another, that means if we just pick out a small element from here, this is the first thing. As because you can see it is acted upon by an axial force and a torsion, so state of stress all along the member will be the same. That means any point along the member of the beam is a critical stress point. Had it been something else, as per the design considerations, what we have to take, we have to find out or we have to search for a critical section, but the situation is little simpler in this particular problem. Now, in this case, if we consider, just have a look into this one, So, obviously, if we are having a look into this one, then we get a something stress like this, okay, and stress like this, and stress coming into this particular manner. So, what we can consider this product, I think we are clear about this free body diagram. Now, if we take a separate location, sigma, this is coming out to be sigma. What we got? We got something like this and something like this. Let us just quickly have a look. Well, this is something downward. Okay. So, that means this is the element you are getting. So, you got the point. First we will put that element and you can name the element. That means the element, suppose we put the element name A, and what it signifies? It signifies that we are analyzing the stress at point A. What will be the value of the sigma? As because this sigma is purely an axial force coming into picture. So, this sigma is P divided by area pi by 4 d square. So, that is equals to 240 into 10 to the power 3 divided by pi by 4 into d square, that is 38 mm square. See, one thing you must be remembering, but just I am just telling you once again that in the design you put the stress in megapascal, you put the dimensions, D means the dimensions rather, in mm, then forces will be in Newton. Okay? So, do not bother about changing to meter, etc., etc. You keep this, just remember these three things. Force you keep it all in Newton, dimensions in millimeter, stresses will be in megapascals. Automatically it will come out to be, we can see it or you can also verify. Okay? At this moment we just come down and concentrate onto the problem. Now, I have just given, that is the reason is in kilonewton, we have transferred it to a Newton, pi by 4, diameter, millimeter dimension, it keeps out to be the same thing. So, this gives you a value of something like that, 211.62 megapascals. So, what is megapascals? Basically, it is Newton per millimeter square. Okay. Now, once we get this particular one, we do not know the value of the tau. So, just have a look through the Mohr circle. This is an explained behavior. So, this is shear stress, it is negative, creating an anti-clockwise as per our notations. So, we get a value something, one value like this, information onto other plane, there is a positive shear and no normal stress, that means it is like this. So, we have this as a Mohr circle. Fine. So, we are having, this is sigma A, this is sigma axis, this is the tau axis, and this is your something is that tau max value. Okay. So, in this case it is sigma A and this comes out to be value S comes out to be sigma B. So, we can write sigma A comma B or people also can do sigma 1 comma 2. Okay, sigma a comma b comes out to be sigma by 2 plus minus square root of sigma by 2 whole square. You understand where from I am taking these values from our earlier lectures on stresses in machine members. Okay. So, if it is considered like that, so obviously this particular term situation is nothing but the radius of the Mohr circle is a tau max value. So, we just for a simplification we write it just like that, sigma 2. So, that means sigma a equals to sigma 2 plus r, and sigma b, this is only to avoid writing so many times, okay, this big expression. So, this comes out to be sigma 2 by sigma 2 minus r. So, what is the value of tau max? Value of tau max in this case will be sigma a minus sigma b by 2, sigma a minus sigma by 2, that is obviously it will coming out to be the value as r, and so if we take up the value of tau max, this is the value of the tau max. Now, let us use maximum shear stress theory. Maximum shear stress, what it says, that if it is sigma a minus sigma b by 2 is a tau max, and this tau max should be equal to the tau, the shear stress value at the yield point. That means what we have seen earlier, that this sigma a minus sigma b by 2 is coming out to be sigma yield point by 2. So, what we get, that from this result, if we substitute, then we can find out this value, and that particular value is, again we substitute back, that means r equals to nothing but sigma yield point by 2. So, that value that value as per the present problem is 250 rather by 2. Okay. So, that means r equals to sigma by, that is 1, or again to be more precise, this is the tau max value. So, tau max equals to coming out to be in this range. So, sigma a, and from here we can find out the value of shear stress. This expression we can, let us compute it. Let us compute in the next sheet. So, what we get? This gives the value of tau equals to 66.55 MPa. Okay, and we know from the basic equation of torsion, this is TR by IP, that equals to T into R is D by 2, the stress level is the maximum at that surface. So, pi d to the power 4 by 32, and this equals to 16 T by pi dq. So, if we use this result, then T comes out to be something like 707 Newton meter. Well, I am avoiding some calculations, just you substitute this value. Okay, this is known, this is known. So, from here you get that T is this one. So, same thing, if we try to if we try to consider by maximum distortion energy theory, what we call it as von Mises criteria. Okay. So, maximum distortion energy theory or von Mises criteria, then what we get, sigma A square minus sigma A sigma B plus sigma B square comes out to be equals to sigma yield point square. We are using an equality sign just to have the limiting value. Okay. And what we found out, that I am just writing in this zone, sigma A was how much, sigma by 2 plus R, and sigma B was equals to sigma by 2 minus X. Okay. So, you recollect, and once we get these two situations, sigma by 2 and this is R, then what we get, that we are getting, we substitute these values. Okay. So, if we substitute these values, then it comes out to be how much, the long expression sigma by 2 plus R whole square minus, and this is minus of sigma by 2 plus R into sigma by 2 minus R plus sigma by 2 minus R whole square, that comes out to be sigma yield point square. So, if we consider this expression, then what we are getting, 3R square, this cancels, okay, the 3R square plus sigma by 2 whole squared equals to sigma yield point square. So, without any further calculations, we can just simply find out from these values, R comes out to be how much, just have a check. Okay. This comes out to be 130.77 megapascals, and this is nothing but square root of sigma beta tau square, and that equals to how much, 250 square, and this gives you the value of tau equals to calculated value of tau is 76.85 megapascal. So, the value of torque, if you compute by the same expression what we got here, then it comes out to be around 828 Newton meter. Fine. So, you see we got a value of tau, and this has got a value of tau. So, as we have seen from our earlier plot and these expressions, it is obvious that this distortion energy theory is little more conservative. Sorry, the other way around, the maximum shear stress theory is little more conservative compared to what we get as a maximum distortion energy theory. So, now it is up to you, the designers, which value you will choose, and more we can discuss about this one in the actual design cases. Okay. Now, this was a problem we just solved considering a steel shaft. Let us find out another problem. 32 mm diameter cast aluminum shaft has ultimate strength in tension 55 MPa and ultimate strength in compression 110 MPa. See, we are just every time we are considering the strength, we are using the word strength because that we have discussed. The material property of the material is its strength. Now, how we equate in the design? We try to find out a stress at a point, and that stress at a point should be equated with the what we call as a strength of the material. All right. So, in the similar manner, if we consider this problem, we can see this is the shaft, and this shaft is acted upon by what? Axial force P 26 kilonewton and a torsion T of the nature as shown it from this viewing, it is in clockwise direction. So, again you can see there is the critical point could be anything along this length of the member. So, we got the idea from our earlier class, I mean just sorry our earlier problem, and that gives you that this is the situation we are having an sigma tau this is like this, this is like this. I think there should not be any change. So, what is the corresponding Mohr circle? We have to find out, well, we can draw the nature, that is not a problem. So, this is your sigma A axis, sigma B axis, this is just, hold on. This is your tau axis, we plot these values. So, this is minus, just like the way we did it earlier. Here will be one point, here will be another point, and we draw the Mohr circle. This is sigma A. So, this is a sigma axis, this is a sigma A point. I am sorry, the sigma A is this point, this is the sigma axis. So, this is the sigma A point, the principal stress, and this is another principal stress point, that is an sigma B. So, we have the calculation sigma equals to how much? 26 into 10 to the power 3 to transform into Newton, then area pi by 4 into 32 square. So, this is pi by 4 d square into this is the area and that one. So, that gives you a stress value of 32.33. Now, we know that sigma A comes out to be how much? It will be sigma by 2 plus r, sigma B equals to sigma by 2 minus r. So, if we consider first maximum normal stress theory, and that maximum normal stress theory will give you 16.16. What is maximum normal stress? That the maximum stress value should be equated with ultimate stress in tension specimen. So, that means it comes out to be R, and that value in tension we got it as 55. So, from here we get the shear stress tau comes out to be 35.32 MPa. I am not discussing more because a similar type problem, only we have changed the theories and the materials, that is all. So, this equals to coming out to be 227 Newton meter. Fine. Now, in the same way, if we consider the Mohr criteria, okay. So, Mohr criterion, then what we are having, just to have a very quick look, this is the situation, this comes out to be something like this, okay. Now, for the given situation, this is sigma A, this is sigma B, you understand this particular value is coming out to be sigma A is sigma by 2 plus R, sigma B equals to sigma by 2 minus R. So, this is sigma B, sigma A, so it's coming out. So, for the given problem, what we find out that this is a line, which should be considered, because we are having the sigma A and sigma B values. And so equation of the line, we can see sigma A by what is this corresponding, it is ut. I am writing ut to find out as ut means tension, minus sigma B, minus sign is already taken care of, so u compressive, and this equals to 1. So this is the value, so you just substitute these values over here. Okay, so if we have substitute these values, then what we get, 16.16 plus r divided by 55 minus 16.16 minus r 110 equals to 1, and this gives r equals to something is 31.28, and that equals to, you know, square root of sigma by 2 whole square plus tau squared, and we get tau equals to 26.78 megapascal, and utilizing the same equations, T equals to 172.3 Newton meter. You can verify the sorry. So you can verify the results. Okay. Hope by your own calculation, just have a check of this one. Anyway, if there are some calculation mistakes, is nothing to worry, because you can correct yourself. But the process what I have just shown you is a method. Now it is up to the designer, but one thing you please note, that in this case the stress at a point is directly equated with the strength of the material. Well, that means what I mean to say is that we found out a stress at a point, okay, in this problem. Torsion direction was something like this. Okay, we find out the stress at a point, and that stress at a point, sigma point or sigma A, say sigma A, was directly equated in some form, I just writing in some form, with a sigma ultimate or sigma yield point, etc., etc. But normally that is not to be done. We should reduce the stress values of the stresses to some extent, and those things are called actually the allowable stress. And what is allowable stress? That means these allowable stresses are obtained from this material property and using some factor of safeties. All those things we will be discussing in our next class. Thank you.